Hello, everyone. Thank you very much for attending. And well, this talk is about vulnerabilities that I found recently in the reference implementation of the TPM 2.0 specification. So the usual introduction, my name is Francisco. I am from Argentina. I'm a reverse engineer and security researcher at Quarks Lab. Before joining Quarks Lab, I worked at Core Security as an exploit writer. And I'm interested in the usual low-level stuff, such as reverse engineering, searching for vulnerabilities, exploitation, and so on. So what was my motivation for this research? Well, one day I was installing Windows 11 on my VMware workstation, and I noticed that there was an extra process running on my host, which was called TPM2MU. And I quickly figured out that it was a virtual TPM. So I thought, I think that this can be a nice target for a virtual machine escape. Like, if this thing parses commands coming from the guest, maybe if I found a vulnerability in this, I can escape from a virtual machine. And something extra is that this is also true for cloud environments, since nowadays, all the biggest cloud computing providers offer you virtual TPMs. Also, I think a TPM is interesting as a target because the firmware runs on a separate processor. So if you happen to get code execution on them, you could have something that like really sneaky and hard to detect because you cannot observe what is going on the TPM. Also, the underlying protocol of the TPM is really complex, and the firmware is typically written in C, so we know for sure that this usually leads to vulnerabilities. And fourth, there's a reference implementation published by the Trusted Computing Group, which is used by most of the vendors. So if we manage to find a bug in the reference implementation, we typically manage to affect a lot of different vendors because they all share the same code base. So this is the agenda for the talk. I'll cover just the basics of the TPMs, then some specifics about the virtual TPMs, then we'll dig a bit into the protocol internals of the TPM 2.0, then we'll go into the details of the two vulnerabilities I found, and then some interesting bits in the disclosure process, which involved a lot of vendors. So for the TPM basics, the TPM is a standard crypto processor. It is specified by the Trusted Computing Group, which is a non-profit organization in which there are many big vendors involved. And it is designed to perform cryptographic operations, such as generation and storage of cryptographic keys. You can use them to do encryption and decryption using both symmetric and asymmetric algorithms. You can use the TPM to generate and also verify digital signatures and to perform secure random number generation. Among the typical use cases, we have attestation of the boot process integrity, just to be sure that the firmware of your computers is not compromised. It is also used to store keys for full disk encryption solutions, such as BitLocker on Windows, and it can also be used for digital rights management, for example. So TPMs come in different flavors. You have hardware TPMs, which is basically a chip. And among the hardware TPMs, you have the integrated ones, which are just integrated with the rest of the components. You have discrete TPMs. If your computer doesn't come with one, but your motherboard has the proper header, you can buy one and connect it to your motherboard. You also have software implementations of the TPMs, which are typically shipped with virtualization software, such as VMware, HyperV, VirtualBox, QEMU, Parallels, and so on. And finally, there's a kind of hybrid version, which is the firmware-based TPMs. These ones run in a kind of trusted execution mode, but within the main CPU. For example, Intel provides what is called PTT, which stands for Platform Trust Technology, and it runs in the Platform Controller Hub. And likewise, AMD provides an alternative that is called AMD FTPM. And as I said, you can find virtual TPMs on all the major cloud computing providers. For example, nowadays, Amazon provides Nitro TPM. Microsoft Azure provides virtual TPMs as part of what they call the Trusted Launch. Google Cloud provides virtual TPMs as part of the shielded VMs. And in the case of Oracle Cloud Infrastructure, you can find virtual TPMs as part of the so-called shielded instances. So, as I said, the TPM, actually the Trusted Computing Group, which defines the specification, provides a reference implementation of the TPM 2.0. So it's basically code that, for the firmware, it is written in C, and it's adopted by most of the vendors, both on virtual TPMs and hardware TPMs, and cloud TPMs as well. There was another standard, which was TPM 1.2, but it's deprecated right now, and the current standard is TPM 2.0. So the reference implementation is quite big. If you visit the site where it is hosted, you will see that there are 6 main PDF files, which, if you sum all of them, there are 2,500 pages, which is a lot. For example, some of them, for example, the last one, supporting routines, code for supporting routines, is more than 1,000 pages. So it's a pretty big implementation, and usually that leads to security problems, because there's a lot of complexity in this reference implementation. So if you start browsing the reference, you will see that the C code for the firmware is embedded into the PDF documents. The Trusted Computing Group does not have like a source code repository. Basically, you can browse the PDF files and see that the code is embedded like this, and it's intertwined with like section names, tables with some information, line numbers, and so on. So it's quite messy. And so where does the reference implementation is kept in? Well, Microsoft extracts the code from all that mess in the PDF files, and it keeps a repository on GitHub. And IBM does something similar, but they keep a repository on SourceForge, which is quite old school, if you ask me. But anyways, if you check the SourceForge repository, they get like some hundreds of downloads per week. So it's still quite active, I would say. And if you check the issues of the Microsoft repository, where they hold the reference implementation, you can find this issue where there's someone saying, I presume, based on this discussion, that the generator parses the TPM 2.0 specification itself to generate code, and they ask if the code is available. And well, the developers say, no, sorry, it's not available right now. And there's someone who is insisting, like, are you planning to make it available? Can you provide the reason, or is it also confidential? Well, it's understandable, because probably it's a bit hacky. They are scraping PDF files and extracting source code from it. So it's quite striking to see that that's how the reference implementation code gets fetched from PDF files. So as I said, the specification is quite complex. As a user, you have user mode tools, such as TPM2 tools, if you are on Linux, which will abstract you from the complexity. For example, let's say you want to issue a command called start auth session. You can check the documentation for the command, and it will show you like a couple typical Unix-like command line things. So basically, you just run a couple of commands and you do an authorization session. But under the hood, the protocol is like really complex. For example, this is just a screenshot of part of the explanation of this command. And you start reading like really complex things like, if both TPM key and bind are null, then session key is set to the empty buffer. If it's not null, then encrypted salt is used in the computation of session key. And it continues like, the TPM shall return TPM RC size if non-scalar is less than 16 octets or is greater than the size of the digest produced by auth hash. And it's really, really hard to understand. It's really complex. So let's move on to the virtual TPMs. So virtual TPMs are like really a gift if you want to do research on the security of the TPM firmware, because basically it allows you to easily debug the firmware. Basically, if you know how to debug native code, you just attach a debugger to a user mode process, either, I don't know, GDB if you're on Linux or HyperV if you're on Windows, and you just debug the code without, I mean, it would be really way harder if you try to do that on a hardware TPM. So when Windows 11 came out, it was a bit surprising that one of the hardware requirements was the presence of a TPM 2.0 module. So this kind of forced like the different virtualization solutions to offer a virtual TPM if they wanted to support the latest Windows operating system. And as I said before, it's just a user mode process running in the host system. The way the virtual TPM communicates with the guest, it really depends on each virtualization implementation. For example, VMware Workstation uses two pipes, one for reading and one for writing. HyperV by Microsoft uses RPC. SWTPM, which is used by QEMU, uses a TCP socket. So everyone does it in a different way. So I said that virtual TPMs are really handy if you want to debug the firmware, and that is true except for HyperV. So if you are asking why, it's because the virtual TPM of Hyper-V runs as what is called an isolated user mode. So basically the code of the TPM firmware is in the TPM UM-DLL, and it is hosted within the BMSP process, which is a virtual machine secure process. So this is done by leveraging virtual secure mode, which uses Hyper-V to create two virtual trust levels. We have VTL0, virtual trust level 0, which is like your traditional mode of kernel mode running on ring 0 and user mode running in ring 3. But on top of that, you have like a secure mode, which is the VTL1, which is has higher privileges, and that is where the secure kernel runs in ring 0 and isolated user mode processes run in ring 3. And one characteristic of this is that it's not possible to attach to an isolated user mode process, let's say the virtual TPM. I took this picture from an article by Microsoft describing how the different virtual trust level work to have an isolated LSAS, which is a pretty well-known process. So we have on the left the normal world where we have ring 0 and ring 3. And on the right, we have the secure mode. On the bottom, we have the secure kernel. And on the top, we have the isolated user mode processes. There we can see the LSA ISO process, but you can just replace that name with the virtual TPM, and that's exactly the model of how it runs on Hyper-V. So how to debug it? I will do just an overview, but I'm preparing a blog post that should be published soonish. So if you're interested in it, you can keep an eye on it. So the way to debug a virtual TPM, you usually cannot, but you can kind of overcome this by using nested virtualization. That is, having a virtual machine running inside another virtual machine. So what I did was a variation of what Sahar Amar explained in a blog post at the Microsoft blog. So the first step is we create a Windows virtual machine. Let's call it the level 1 virtual machine. And in the guest system, we install HyperV. Then we launch HyperV in the guest, and we use it to create another virtual machine, which is nested. Let's call it level 2 virtual machine. And this level 2 virtual machine will have a virtual TPM. The third step is to enable hypervisor debugging on the level 1 virtual machine, and we attach the debugger to it. Once we are debugging the hypervisor on the level 1 VM, we put a breakpoint on the handler of a hypergoal, that is a service offered by the hypervisor that is called HBCall-BTL-return, and it is used to transition from BTL1, that is the most privileged mode, to BTL0. So when that breakpoint hits from a register, you can retrieve a pointer to some HyperV structures. You walk these structures, and you retrieve the instruction pointer from where the hypercall was called, and this virtual address belongs to the secure kernel. You can subtract a delta, and you obtain the base virtual address of secure kernel. You do a page walk to transform that base virtual address into the base physical address of secure kernel. And finally, you patch in physical memory the function that is called SKP, is process debugging enabled, so that it always returns true. If you force this function to always return true, you can attach to isolated user mode processes. So it's a bit convoluted, but it allows you to debug isolated user mode processes in your research environment with nested virtualization. So let's move on to the TPM protocol internals so that we can later understand the vulnerabilities. So first, let's take a look at the format of the commands and responses when you are communicating with a TPM. So this view is like a really simplified view of how you communicate with a TPM. On the upper part, we have the main CPU, and on the lower part, we have the secure environment with the TPM. So your application running on user space opens a TPM device, which is offered by a TPM driver. On Linux, it's called /dev/tpm0, and on Windows, it's /?/TPM. So you open a handle to the device, and you start sending commands, and the TPM driver will perform I/O and send the commands to the TPM, and on the other way back, it will receive responses and forward them to the applications. So every TPM command starts with this base header. It's 10 bytes in size. It starts with a tag, which is 2 bytes. The tag indicates if it's a command with no sessions attached, or if it has sessions attached to it. Then we have 4 bytes for the size of the command, and finally, a code for the command that we want to invoke in the TPM. And just for reference, there are around 110 commands supported in the TPM 2.0 specification. So after the base header, you can have handles. But this is dependent on each command. Some commands may need 1 handle, or 0, or 2, or 3. I mean, it's from 0 to 3. And they basically use those hard-coded values, like admin, operator, transport, owner, and so on. So this is variable in size. You can have from 0 to 3 handles. After handles, you find what is called the authorization area, although it is also interchangeable called the session area. So it's composed of 4 bytes, which indicate the size of the authorization area, followed by the authorization data right at the bottom. And the authorization area or session area is only present if the command has the TPM ST session as the tag. And finally, again, this is command dependent, but a command can be followed by parameters. The parameters start with 2 bytes indicating the parameter size, followed by a variable number of bytes for the parameters. So that was about the commands that you send to a TPM. So let's see what's about the responses that we get from a TPM. The basic header is quite similar. We have a tag, which are 2 bytes. The size, the total size of the response, and a response code. It is 0 if the request was successful, or non-0 if there was some kind of error. So same as we could have like some variable fields, such as a handle area, parameters area, and authorization area in a request. A response can also have these variable-sized and optional parts. The interesting part, and don't ask me why, but in the response, as you can see, like the parameters come first and the authorization area comes after. I don't know why, but it's like in the inverted order if you compare it to the requests. So let's dig a little bit into the authorization area, because it will be relevant for the bugs that we are going to see. So an authorization area looks like this. We have 4 bytes for a session handle, a field called the nonce size, followed by as many bytes as the nonce size value was. Then we have a very interesting field, which is the session attributes, which is a bit field. And you can see the different fields on the right, followed by an authorization size and as many bytes as the authorization size value at the end. So regarding the session attributes, you can see highlighted in yellow that there's an attribute called decrypt. If this bit is set to 1, that instructs the TPM that the parameters that follow the authorization area must be decrypted before being used. Likewise, if you set the encrypt bit, that instructs the TPM to encrypt the parameters before sending them back in a response. So what is the smallest authorization area? Well, we can set the nonce size to 0, so there's no nonce. We can set authorization size to 0, so there's no authorization data. So this is like the smallest one that we can build. When I was trying to hit some code that looked suspicious, I just was trying to build the smallest one, because understanding all that you need to reach a certain point, it was a bit complex. So I always, in order to make a proof of concept, I always try to keep it as short as possible. So this came very handy for what's next. So let's dig into the vulnerabilities themselves. So the first bug I found was an out-of-bounds read in the crypt parameter decryption function. And it was assigned .cb, it's 2023-10-18. So this code is part of the TPM firmware, and it gets executed when the TPM firmware is parsing your commands. So we are in the execute command function, and the code performs some sanity checks. Highlighted in yellow, you can see that it's checking if the authorization size value, if it's smaller than 9 or greater than the rest of the data, it detects that it's some abnormal condition, so it returns. So that's fine. Here it's, if you remember from the previous slide, it's checking that the authorization size is not smaller than the smallest authorization area that it can handle. But let's say that we pass that check. So execution continues here. So at 2, it needs to calculate where the parameters start. So the parameters start where the session buffer or authorization buffer starts, plus the authorization size. That is, parameters start after the authorization area. And then at 4, it calls parse session buffer, and you can see here at points 5 and 6 that it's passing a pointer to the parameters area and the size of the parameters area. So let's see what this parse session buffer function does. So at 1, it's checking if the decrypt flag was set in the bit field, if you remember from a few slides ago. So if we have set that bit, we enter that if condition, and basically it propagates the parameter pointer and the parameter size to the crypt parameter decryption function. So let's dig into this function. So the crypt parameter decryption function starts there in yellow by using a macro called byte array to uint16 in order to read the first 2 bytes of the parameter data, which is supposed to be the cipher size. That is the length of the data that needs to be decrypted. If we see the definition of that macro, we see that it just reads 2 bytes, and it returns it as, not returns it, it builds a 16-bit value by reading 2 bytes. So what's the problem here? It is using that macro to read a 16-bit field from the buffer pointed by the parm buffer start without checking if there's any parameter area past the authorization area or session area, it's the same. So basically, if we send a command that doesn't contain a parameter area after the session area, we will trigger an out-of-bounds read, and the TPM will access memory past the end of the command. The problem here is that they were using this macro, which does just it just accesses memory without doing any bounds check, and they should have used the uint16 unmarshal function. And actually, they have a lot of helper functions to unmarshal stuff because it's a binary protocol and they need to unmarshal a lot of different structures. So actually, they use these helpers everywhere, which perform proper size checks before reading, but here they just forgot and they just did some direct access, and that leads to the out-of-bounds read. So for me, it's always easier to explain this in a visual way. So this is the kind of command that we need in order to trigger the out-of-bounds read. We have, as always, the base command header. We have the handles that is needed by a specific command, followed by the authorization area, and we just omit the parameter area. That parameter area is assumed to be present, so it attempts to read the 2 bytes that are supposed to be the param size. So that's exactly where the out-of-bounds read happens. This is the function that I said that they should have used. Actually, they use it everywhere, but here they just forgot. They have this kind of API where they give a pointer to the buffer that they are parsing, plus a variable that is keeping track of how many bytes there are left. So these helper functions update the size so to keep an updated length of what is left. So at first, this one checks if there's not enough data to read a 16-bit value, it just returns an error. So by replacing the macro with the call to this function, they fix this actually. This is a visual representation of the steps that you need to perform in order to trigger this out-of-bounds read. So first, you need to send an start auth session command to the TPM. If everything goes well, the TPM will answer with a success response code, and it will return a session handle. In this case, it's just 20000 in blue. Finally, we need to send another command to the TPM. And here we need to send a command that supports parameter encryption. In this case, to build the proof of concept, I used the create primary command, but there are a few others that support parameter encryption. As the session handle, we need to send the session handle that was returned by the TPM in step 2. It's important to set the decrypt flag to 1 in order to hit the vulnerable code path. And that's it. That way, you can trigger the out-of-bounds read. So let's continue with the next bug, which is an out-of-bounds write in the same function. But this one is more interesting than an out-of-bounds read. So we are exactly at the same vulnerable function that I showed before. We are in crypt parameter decryption. In line number 1, this is where the first bug was located. We see that it reads the cipher size, which is 2 bytes, and then it advances the buffer by 2. That's it. That's what it does in the next line. So far, so good. So after that, it performs a sanity check. If the value of the cipher size is greater than the length of the remaining data, it returns an error. That makes sense. After that, at 4 or 5, it calls the function that does the actual decryption of the parameter data. You can use 2 methods to encrypt and decrypt the parameters. You can use XOR, exclusive or you can use a symmetric block cipher. In any case, in any of them, you can hit the vulnerable function. You can hit the vulnerable code. It's not really relevant which method you use. So what's the problem here? I forgot to mention that when calling either crypt XOR obfuscation or param decrypt sim, it is passing a pointer to the buffer and its size. So what's the problem here? The problem is if we provide a proper parameter area, that is, we avoid the first bug here. If we do that, the first 2 bytes are read, and the buffer is advanced by 2. That is, OK, we have just parsed the cipher size. We need to move on 2 bytes after. There's an attempt of a sanity check, which is here. Like, if the value of cipher size is greater than the length of the remaining data, it returns an error. But the problem is that after it reads the 16-bit value of cipher size and advancing the buffer pointer by 2, it forgets to subtract 2 from buffer size to account for the 2 bytes that were already processed. So as a consequence, it's possible to pass the sanity check, that is this sanity check, with a cipher size that is larger by 2 than the actual size of the remaining data. So when either crypt XOR obfuscation or param decrypt sim is called to decrypt the data in the parameter area, the TPM ends up writing 2 bytes past the end of the buffer holding the parameter data, which results in an out-of-bounds write. But again, this is easier to understand in a graphical way. So this is the state before parsing the parameter area. Let's say that we have the cipher size value, let's say it's 58, because after it we have 58 bytes, like A, B, 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 C, 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 C. So the total size, the length of the remaining data to be processed is 60. So far, so good. So after reading the cipher size value, this is the expected state, what should be done. Like, OK, the buffer pointer is moved by 2 to the right, And the length of the remaining data should go from 60 to 58, because we subtract that we have already processed 2 bytes from the cipher size value. This is what should have been done. But the actual state is like this. After moving the buffer pointer, after processing the cipher size value, the buffer size variable, which holds the length of the remaining data, is not updated. So we have updated the buffer pointer, but the length of the remaining data is still 60. So the length of the remaining data is now considering the 58 bytes we have here, plus whatever 2 bytes are right after the parameter area. So, as a consequence, we can have this wrong state considered valid. Like, we can craft a parameter area like this. We can have like 58 bytes here in the purple region. We set cipher size to 60, which is a wrong value because we only have 58 after it. And when it does the check, when it checks if cipher size is greater than the length of the remaining data, and then it tries to kick us out, it says, okay, 60 is not greater than 60, so this thing is fine. So when it tries to decrypt this parameter, either using XOR or asymmetric cipher, it will end up decrypting all the purple area plus the 2 bytes right after that. So how do we reach that code? Well, again, we need to send first an start auth session command. The TPM answers us with the response code of success. We get the session handle. In this case, it's 200001. And as the third step, we send a create primary command. We pass the same session handle that we received in the previous step. We set the decrypt bit to 1. And in the param size field, which is the same name for cipher size, we set it to the maximum command size that is supported by the TPM, minus the size of all the headers that are before, plus 2. And this way, we will be able to write 2 bytes after the end of the buffer that is used to hold the TPM command. So, what is the impact of the vulnerabilities? Well, regarding the first bug, that is the out-of-bounds read, the vulnerable function reads 2 bytes past the end of the received TPM command. So if a given TPM doesn't zero out the command buffer between different commands, it can read whatever 2 bytes were already there from a previous command. But this is really dependent on the implementation. For example, in the different virtual TPMs where I tested it, VMware doesn't clear the command buffer between different requests, so the out-of-bounds read ends up reading whatever 2 bytes were already there from a previous command. In the case of HyperV, for every request, it pads all the unused bytes up to 1000 in X with zeros. So the out-of-bounds read just reads a couple of zeros. So it's like really harmless. In either way, I didn't, even in the case of VMware, even if I was like reading 2 bytes from a previous command, I wasn't able to do anything really useful to that. I wasn't able to exfiltrate it or retrieve them. So I wasn't very happy with that. So this wasn't very impactful, but that's it. This is a screenshot of what the out-of-bounds read looks like in Hyper-V. So the actual TPM command that I sent is there highlighted in green. And right after that, it tries to read the 2 bytes that are after my actual commands. and it's just a couple of zeros, so pretty harmless, if you ask me. The impact of the out-of-bounds write is a bit more interesting, because always corrupting memory is always dangerous. So what can you do with the 2 bytes overwrite? Well, the thing is that even if all the implementations share the same vulnerable function, the thing is that the buffer that is like overflown is specific to each implementation. And each one, again, does it in a different way. So you have to check every implementation to see if you can find something useful adjacent to the command buffer that you are writing past. For example, VMware supports a TPM command size of 1,000 bytes in X. However, they use an oversized buffer of size which is 10 times bigger, which is 10,000 in X. So basically, you are writing past your command, but it's just there's nothing relevant after. It's just an oversized buffer, so you are not writing any adjacent data. Even if it doesn't look good, you are not overwriting anything. So that was a bit frustrating. In the case of HyperV, they use a static variable for the command buffer. Its size is 1,000. And here, there is something interesting in that for a long time, there has been some kind of exploit mitigation that is added by some compilers, which is called variable reordering. So basically, when you have like an array of chars, which are kind of prone to being able to being vulnerable to a buffer overflow, they usually move the arrays of chars to the end of whatever variables they are handling. So if you overflow that by maybe a couple of bytes, you are not overwriting anything that is adjacent. So again, in this case, the compiler kind of saves the day for Microsoft. So I wasn't able to achieve much in HyperV as well. The one that looks more promising from an exploit writer perspective is SWTPM used by QEMU, because it uses malloc in order to allocate the command buffer. Again, the maximum command size is 1,000 in X, but SWTPM supports something that is called a command prefix, but it doesn't really matter because it allocates 1008, and you can send up to 1008 bytes between this prefix and the 1000 bytes of the command. So in SWTPM, you are actually able to write past the end of this buffer on the heap. So that's definitely the one that looks more promising if you are trying to exploit it. So what can you do with this? Well, using an out-of-bounds write, in the best case or worst case, depending if you are trying to write the exploit or you are trying to protect your TPM, this could lead to code execution. Even if the primitive is a bit limited because you can write just 2 bytes, but there have been cases where like a very limited write primitive can be used to get full compromise of a target. Actually, for example, my colleagues Damiano and Maxime last year presented here an attack on the Google Titan M chip, and they had a very limited primitive which allowed them to write just a byte with value 1 to an address, and they managed to abuse it to get full compromise of the Titan M chip. With the out-of-bounds write, in the best or worst case scenario, you could get code execution on the TPM. And if it's a virtual TPM, you could maybe abuse it to escape from the guest and execute code on the host. And of course, it may also have an implication on cloud computing scenarios where you could maybe escape from your instance and compromise the host, which would be like a very scary scenario. But sometimes, in this case, to be fair, I didn't spend much time trying to go for the exploit. I had already spent quite some time doing the research, and then I had to move on to some other work. So I kind of stopped there and didn't go for the full exploit. But even, let's say, if I'm not able to use the Autophones, right, for remote code execution, sometimes in this kind of scenarios, like what is supposed to be a secure crypto processor, maybe having some other limited results may be impactful as well. For example, let's say I'm not able to get code execution, but if I manage to overwrite 2 bytes containing sensitive data, such as a key that is held in the TPM memory, maybe that can have a big impact. And even causing a denial of service can give you enough trouble. I will go back to this a little bit later. Because if you manage to crash the TPM by using this, you can maybe make a BitLocker or other full disk encryption solution to fail if it cannot access the key because the TPM is not responding anymore. And if you're using your TPM to perform boot attestation, if the TPM is not available when booting or rebooting, it will fail to do that. So it may cause like a kind of permanent denial of service. It's not a problem if it's your physical computer, like your laptop, but if it's some server and you don't know where it is located and you need to go and unplug it so that it can start again, it may be a little bit complicated. This is just a screenshot of what the Autophones write looks like in HyperV. The line in yellow divides, like on top of it, we have my actual parameter data. It's just a bunch of A's. And the 2 bytes highlighted in green, they not belong to the parameter data. However, after triggering debug, you see that they are overwritten. So there you can observe the Autophones write. So to go to the final part of the talk, some interesting details about the disclosure process. So it was an industry-wide disclosure process which involved a lot of parties. Ivan Arce, a colleague from Quarks Lab, handled it from our side, and it was coordinated through the CERT. Overall, they were all quite cooperative, so it was a good experience, even if it was complex. Something that happened is that, like, the day we reported the vulnerabilities, the CERT gave access to the details to around 40 vendors, among some software vendors, such as Microsoft, VMware, and so on, and some hardware vendors, which makes sense, which are the vendors that make hardware TPMs. And like 2 days later or something like that, we saw that the CERT gave access to the details of the vulnerabilities to 1,600 vendors, and among the vendors, you could see like 7-zip, like this tool that you use to unzip files. They have access to the details of these TPM vulnerabilities. And the reason for that, they said that it was because many hardware vendors wanted to reach out to some of their suppliers up and down in the supply chain. So since it is quite a hot topic these days, the supply chain security, like it was open to virtually all vendors. In those cases, of course, we were a little bit worried about having leaks before the embargo ended, before different vendors had time to patch the vulnerabilities. And actually that happened. Google ended up pushing fixes to a Chromium OS repository, which is public, before the embargo ended. So if someone was, which probably happens, if someone was monitoring commits to see if there were security-sensitive commits, they probably were able to identify this before it was patched for the rest of the vendors. There's also a Linux distribution called OpenEuler, which is like a kind of open branch of some Huawei Linux form. And again, they also made the report available in their public issue tracker. So we had at least 2 leaks before the embargo ended. something that was very curious is that on all the software implementations that we checked, we could verify that they all were affected by the vulnerabilities. However, some hardware vendors told us that their product were not affected. The thing is that it's hard to verify independently because you don't have any debugging or observability capabilities on a TPM, so you have to blindly trust them. Like they say, oh no, our firmware is not affected, and you don't have a debugger to debug and see if you are overwriting memory after the TPM command and so on. And if they already, it's curious because it looks like everyone, either they have their own implementation and they are not using the reference implementation, which would be a bit weird, or they already identified the bugs and fixed them, but they didn't report them up to a trusted computing group. And some hardware vendors, which seem to build TPMs, are in an unknown status, so they didn't say either if they are vulnerable or not. So in this page, that is like a huge index of the different status of the different vendors. They are kept as unknown. So for the conclusions, every TPM that is based on the reference implementation, either software or hardware implementations, were affected, or we were expecting to be affected by these two vulnerabilities. Also, even if all the different implementations share the very same vulnerable function, the possibilities of successful exploitation are very implementation dependent because the buffer that holds the TPM command is left to each implementation. Like the reference implementation doesn't tell you how you receive a command and how you store it. So you decide how to do it and you just pass it to the APIs. And everyone does it in a different way. VMware pre-allocates an oversized buffer. HyperV allocates a variable buffer. SWTPM used by QEMU uses a buffer in the heap, so it's totally different on each one. Well, as I said before, all the major virtualization solutions that we checked were affected. The one used by QEMU is the one that looks the most dangerous because it's a buffer in the heap and it is the exact size of the maximum TPM command size. But I haven't checked on other solutions such as VirtualBox or Parallels Desktop because, as I said, I moved to other things. Something very interesting is that virtual TPMs that are available in some of the biggest cloud providers were also likely affected, and probably we were quite confident that at least Google Cloud and Microsoft Azure were affected. And you may ask why. Well, there's some blog post when Google Cloud announced that the availability of virtual TPMs, and they said, oh, we use the reference implementation provided by IBM with a link to SourceForge, and we checked that that version contained the vulnerability. And in the case of Azure, it is based on HyperV, which was affected, at least on the version that you can have on your computer, either on your laptop or on your servers. It's a bit unknown about Amazon because we don't know what Nitro TPM is based on, and we don't know either on Oracle infrastructure. Also, it's very interesting that we were able to trigger and verify the presence of the Autophones write in at least one hardware TPM. It was a Dell machine, a Dell Latitude E5570, having a Nuvoton hardware TPM. And basically, after triggering the out-of-bounds write, the chip would stop responding to further commands. And in order to make it to have it working again, you have to do a hard reboot, like powering off your computer and then starting again. A soft reboot was not enough. So that was a case where we were able to verify the presence on a hardware TPM because we made it stop responding. Something that is very important, at least from a point of view, is that it's very, as I mentioned before, it's very hard to verify the presence or lack of in hardware TPMs because you don't have any debugging or inspection capabilities. So you cannot debug functions and see if you are overwriting memory or whatever. Unless you make it crash, just like we did in the Dell Latitude, you don't have any visibility of what is going on. If it doesn't manifest as a crash, you don't have idea if you're overwriting memory and not triggering the cache or what. Finally, last conclusion, I think that reference implementations deserve very special attention regarding their security, because a vulnerability in a reference implementation spreads across code bases, so they end up affecting a lot of vendors, because all of them, I mean, you have to find the bug in a single code base, and you can affect a lot of different vendors, which seem to be unrelated, but they share the exact same code. So that's it. Thank you very much. Do you have any questions?
All right. Thank you very much for this very interesting talk. So if you have any questions, please show hands. I don't see any questions so far. No?
No questions? Oh, there.
Thanks for the talk. When looking at the reference implementation code, did it seem to you that it was generally well structured, or are you like, well, I only found these 2 bugs, but there's probably still more out there, or do you think, well, the chance of like it being a very high value research field is quite low?
That's a very good question. One thing that happened to me is that the code is, how to say it, it's the TPM thing as a whole is it's very dependent on like states, like it's a very stateful thing. So I was able to audit some code that I was able to figure out how to reach, but there are some parts that it's really complicated to understand how to reach them. So maybe I just kind of scratched the surface. In what I saw, it looked kind of good, I'd say. For example, they have a lot of these helpers to unmarshal stuff, and actually it is automatically generated. They don't do it by hand, so that's a good thing. So that part looked solid. However, what worries me the most is like the complexity and the complexity of the states. And there are some parts that are probably very hard to reach. And now that you mentioned that, when I was first searching the implementation, the reference implementation, I stumbled upon a copy that is held in the Chromium OS repository. So that's the first one I downloaded. And when browsing the code, I saw that there was like a folder called fuzzing, and there was some template using libfuzzer from LLVM, and it was Google, and I said, oh, okay, so Google is fuzzing it, and I was quite discouraged, like, okay, if they are fuzzing it, probably I'm not going to find anything. When I find this, I realized that probably they were doing just a very, from the template that I was seeing, they were doing some like very basic fuzzing, like, but they were not doing anything having in mind like all the complex states that the TPM can switch from one to another. So I guess that I'm not saying that it's impossible to reach those by fuzzing, but you're probably hitting a lot of trivial cases where your inputs are being discarded. So my guess is that even a fuzzer is not hitting deep code, because it would be definitely better to have something stateful and knowing all the transitions. And like, for example, to reach this one, like this, the vulnerable function that I found, you have first to start an authorization session with some given parameters. The TPM returns a session handle, you need to reuse that, and so on. So I mean, maybe, yeah, after some millions of tests, you can reach that by luck. but you're probably spending a lot of time being rejected too early. You would need to check like your coverage and not just leaving it run like with a very basic template using libfuzzer. So in my opinion, maybe it's a bit under-audited. So probably there has to be more things hiding in there.
All right, thanks for the answer.
Thank you.
All right, are there other questions? That doesn't seem to be the case. So again, thank you very much.
Thank you very much.